Hello friends, today we are going to discuss about one of the important topics in electronics. You have been learning about electronics, though not learning, you have been using it all along. But we don't know exactly what is involved in these electronic gadgets that we use every day and also how they function. So to find out exactly what is going on between these within these apparatus or appliances that we use, there are like small components which are called devices, or as you call it, kind of the nuts and bolts of the system which make these systems work the way we want them to work. We have been using radios, television, we have been using mobile phones, whatnot. In our kitchen we are using like refrigerator or washing machines also, which are also now programmed and controlled in using electronic devices. You have Walkmans, you have laptops, you have power supply generators, you have mobile phones. Everything is nowadays run with semiconductor devices. These are the ones that they actually workhorses of all these things. Left hand side below is a typical integrated circuit or a transistor. Then here are also some integrated circuits, and these integrated circuits are now put here on what is called a board or electronic circuit. So this is what is now the actual happening or the happening thing in the electronics. The device size, as you are seeing, is very small. Capabilities of these devices is much better with respect to the vacuum devices, and they also work on much lower voltages. If you remember, in case of vacuum devices, we needed something like 300 volts or more volts to work. Here we are working with something less than 5 volts, sometimes 30 volts, but nothing more than that. They are all running on what is called semiconductors. These are the materials whose resistivity values lie between those of conductors. Conductors means the metals who have like their resistivity in the range of micro ohms centimeter, whereas they are also like between the insulators. Insulators are something like something that does not conduct. Okay, the ceramics kind of things, where the resistivity values are much higher, like 10 raised to 8 ohm centimeter kind of thing. So to give you just the idea about different materials and values of resistive values, I have put here two typical silver and copper, where you have micro ohm centimeter resistivities. Then you have germanium and silicon. The yellow ones here are the materials where you have the values in ohm centimeter, 46 ohm centimeter, 6.4 ohm centimeter. And then I put some values for glass, quartz, which are the insulators, where the values run in 10 raised to 12 to 10 raised to 16 or sometimes 10 raised to 19 ohm centimeter also. So essentially we are interested in these devices which are shown with yellow color here, the semiconductor devices. Now what are these? These are the elements who have a crystal structure in which each atom is connected to 4 neighboring atoms, and it has got some tetrahedral bonding with it, and there is no free carrier, because if you see, each one of these has got 4 outermost electrons in its own unfilled shell, and since it has got 4 neighboring atoms also who are sharing, one electron is being shared by this atom, another is shared by this atom, third is shared by this, and fourth is shared by this, effectively completing the shell of 8 for this. And so there are no free carriers in this in case of intrinsic semiconductor or semiconductors at 0 degree, and so you don't get, the resistivity value is quite high at that point. However, if you increase the temperature, then you get some kind of bond breaking and some electrons get ejected. Now what happens when electron get ejected here? It remains one void here, or a deficiency of electron, which is called hole. So you have two types of conductors in case of semiconductors. One is the electron and deficiency of electron, which is called hole. Here I have shown another small diagram which you are seeing here on the left hand side of the figure, and it is essentially what is called the energy level diagram. In case of a semiconductor, we have two bands in which the bottom one is called valence band and the top one is called conduction band. If there are any conductors or electrons in the conduction band, then it is free to move and then it is something like a metal. However, in case of semiconductors, what you have is that in valence band, all the valence band levels are filled, but there is nothing in the conduction band. As you are saying, everything is filled here. And so you get a situation where you don't have any free carriers, and this level, which is called Fermi level, lies between an energy gap. The valence band and conduction band, the gap between these two is called the energy gap. In case of metals, there is no energy gap. The electrons are free to move in the conduction band, whereas in case of insulators, this gap is so large that you cannot excite any of the carriers from say valence band to conduction band. However, in case of semiconductors, this gap is of the order of its thermal effects or so and so forth, that you can excite certain electrons from valence band to conduction band by applying say temperature, and you get conduction. So this is exactly what I was telling you is about the intrinsic semiconductor. But what the intrinsic semiconductor is not completely useful or a complete remedy for everything. We need to have control on the conductivity in more better way, and in that case what we have done is add a small amount of another element in these semiconductors. And if you have a different valency, because in case of silicon or germanium the valency is 4, now if we add different valency like valency 3 or valency 5 elements, then we can create some extra charge carriers or means like electrons or holes. This process of such addition of elements is called doping, and this concentration of doping is very small. Like typically if a crystalline intrinsic silicon has say 5 into 10 raised to 22 atoms per centimeter cube, then the doping concentration is as small as 10 raised to 18 per centimeter cube. So it is very small amount that we are adding. But what happens? See here, I have added in this particular case a trivalent element like boron or aluminium or indium are typically the trivalent elements. Now if you add them in this particular matrix that we were seeing earlier, what happens here? For example, if this is some say boron atom, then now since it has got only 3 trivalency, there is a vacancy because it can cater to its 3 neighbors very well, but it cannot cater to this neighbor. So this neighbor is left high and dry, and we have what is called a hole or a deficiency of electron here. And this kind of deficiency is actually a creation of a carrier. In p type of semiconductors, holes are the majority carriers responsible for conduction. Now on the other side, if I like dope the semiconductor with a pentavalent or valency 5 elements, then in that case what is happening? Now valency 5 means like phosphorus, arsenic, these are the pentavalent elements. They are the ones that are called donors, because now if I got say this atom as a phosphorus, then it has already shared 4 electrons with its neighbors. However, still because it is pentavalent, it has still been left with one more additional electron which it can donate to the crystal for conduction. So in this case the carrier is electron. So in this is we called as n-type semiconductor, and in n-type semiconductors the electrons are majority carriers responsible for the conduction. Now what is the use of just one kind of semiconductor? For example, as we saw that the resistivity of the semiconductor can be determined by the temperature, because if we give the temperature or heat the semiconductor, then its temperature gives rise to some electron holes which are generated, means it breaks some bonds and it allows the electrons to get into the matrix for flow. In that case, we can have a device which will be responsible for measuring a temperature, and it is essentially, this is the one that I have shown you here. It is a single semiconductor block which is used as a temperature sensor because its resistivity is temperature dependent. And a typical temperature sensing device made of a semiconductor is called thermistor. So these are the typical three kind of encapsulations or types of thermistors that are available in market and which you can use for measuring temperatures, say up to almost like 1000 degrees Celsius very easily. But apart from that, there is not much use of just a single type of semiconductor. However, if we join P and N type of semiconductors to form a junction, then we have a good tool in our hand to manipulate the flow of electrons as well as make the device work the way we want it to work. So in this case, I have shown you here a p-type region and an n-type region. As you know that in p-type region, holes are the majority carriers, and in case of n-type region, electrons, the black ones, are the majority carriers. Now these positive circles that are shown here or negative circles that are shown here are the ions from where these carriers have left. Okay, so these are the kind of resident ions there. But when you join these two things, what we know is that in p region we have holes as the majority carriers. In case of n region we have electrons as majority carriers. When we join these two, these holes and these electrons that come, they can rejoin or combine, and then there is a region here in between just near this junction which is completely devoid of any type of carriers. You have only resident negative and resident positive ions in this region. It is called a depletion region. Now since from p side you have negative ions and in case of n type you have positive ions, you get effectively a barrier potential which is across this depletion region. Now why depletion? Because it is depleted of any of the carriers, that's why it is called a depletion region. And this generates a kind of a small potential or a voltage which further stops any movement of, say, any electrons from this side or any holes from this side. And then that's why you get a no charge region or a depletion region here. Now if we talk in terms of the energy level diagrams, we have in case of p-type semiconductor more holes which are residing in the valence band, and in case of n-type semiconductor we have many electrons which are residing in the conduction band. And effectively because of these additional carriers, the Fermi level that we had seen in the earlier case of intrinsic semiconductor which was lying in the center is now shifted. In case of n-type it goes towards the conduction band, in case of p-type it comes towards the valence band. So if when we are joining the p-type and n-type semiconductors, essentially what is happening is that you see there is a difference between the levels of the Fermi here. But whenever any two materials are joined, then the property of solids is that the Fermi level tries to match. Okay, that means in this case when we have, say, p-type and n-type, we get a kind of a Fermi level which is matched. In order to do that, as you see, this Fermi level was here which is near the conduction band, here this Fermi level which is near the valence band. When you are matching these two, in order to do that, the valence bands of the two and the conduction bands of the two, if they want to match, they have to bend. They are bending the bands and forming the kind of a depletion layer here, and you are going to have a Fermi level which is matched here. Now this band bending is also very useful when we are going to discuss about the electronic devices that are at work. Another aspect I will just cover in small here is the electrical characteristics of a diode, which you already know. If you give, say, this is a p-type and this is n-type. So if you apply a positive potential to p-type and a negative potential to n-type, essentially you are pumping in electrons from here, which are the majority carriers, which allow and go into the p-type region, and effectively vice versa also. Okay, so you are actually aiding or assisting the flow to happen. So in this case you start getting initially, of course, this here on this curve, if you see, in this case you don't see much of the current because you have that depletion layer where the barrier potential is there. But once that barrier potential is crossed, then suddenly you get rise in the current with even small change in the voltage. This is the forward bias of a diode. In case of reverse, however, now if you apply negative to p type and positive to n type, then in that case these charge carriers just try to repel from each other and your depletion region is actually widened and there is no flow of any current, and so in the reverse bias you don't see any much of the conduction up till this point. Of course, here if you apply higher and higher and higher voltages, at certain point you will just break this barrier and you will have a free flow of current, but in that case you have damaged the device, you cannot retrieve the device. So now you see that in forward bias you got current, but in reverse bias you don't get. Isn't it something like just the vacuum diode that we saw just now? Yeah. So here also we get rectification. This is exactly what is shown here, how the rectification is working. AC source if you give, then on the half wave rectification you get only half positive cycles, and this is called a full wave rectifier, but that we will be discussing at some other point of time. Apart from rectifier diode, there are some types of diodes also. One is a tunnel diode, where you can actually, like, inculcate a kind of a negative resistance region by monitoring or by engineering the doping levels, and in this case this is a kind of a tunnel diode where in energy level diagrams, if you see that initially these are the diagrams where the Fermi levels actually are so degenerate that the Fermi level of one type is going below the valence band, another is shooting inside the conduction band. So you are going to get a kind of a degenerate states here. However, when you apply potential to this kind of diode, then whatever void you are seeing, the valence band in Fermi level here and this valence band and Fermi level, here there are electrons, here there is a void. These two, when they align because of potential, then you get a flow of current, and this is what is called tunneling. Now because of this, initially just diode would have just gone like that. However, because of this tunneling, suddenly with even a small voltage you get a rise in the current, and then when you further increase the voltage, since this tunneling region has passed by, then you start getting reduction in the resistance and again normal diode characteristics are visible. This is a tunnel diode which is used in microwave generation, and this is the symbol of a tunnel diode. Another is a Zener diode. In Zener case also, it is in forward direction, it just works like normal diode. However, in case of reverse, it is not just because of the damage that it happens. However, the thing is that you can have a controlled breakdown of the device which allows a reverse current to conduct, and once you reduce the voltage again it comes back into a cutoff. This happens because of the potential that you are applying across the junction, which is the depletion region, because of very heavy doping. In case of a PN semiconductor diode, if the standard rectifier diode, if you apply a very high doping level, in that case the depletion layer thickness is very small, it's a very thin depletion layer, and so when you apply potential or voltage across that thin depletion layer, the effective electric field across the that layer is very high, which breaks certain bonds and frees some carriers and allows a flow to take place. This is called the avalanche current in this case. So this is a Zener diode which is used in many of the voltage regulator circuits, because if you see this VZ is a fixed for a Zener diode, and come what may, it will always be giving you a constant voltage across it. Another very enlightening and interesting use of diodes is light emitting diodes, where these are the typical diodes that you have seen many a times on traffic signals or on 7-segment displays or calculators also, and these are essentially the ones where you are going to apply a potential, and when some electrons and holes, you are allowing to movement of this particular thing, and when they come back from conduction band to valence band, they emit a photon, and that's why you get a LED, which is a workhorse. So these are the devices that we have talked about today, which are the essential electronic devices. Thank you very much for your attention.